Hello, let's get started. First, I propose to find out what Vellum is and what capabilities does it have. So, Vellum is a simulation framework that uses an extended position-based dynamics approach. It can be used to create many different things including cloth, hair, soft bodies, balloons, grains, and of course they are all able to interact with each other. The main advantage of a position-based approach is its controllability, stability, and ability to produce believable results quickly. There are two approaches to set up a Vellum network. First is the classic approach, when the entire setup is built in a dynamic context, which is used in most aspects in Houdini. Now I'll quickly demonstrate how it looks, and then we'll talk about the second approach, which is much easier to understand and more practical for these types of simulations. Well, now let's create a very basic cloth setup. For this we need some geometry. I will use the grid. Let's call it cloth. To turn it into cloth, I will use the Vellum shelf tools, so click on the Vellum cloth icon, select geometry, and press enter. That's it, Houdini has created a dynamic network for you, and this is how it looks like the simplest cloth setup in DOP. Similar to other types of simulation networks, there is a Vellum object node, a Vellum solver, and of course, a Vellum source node. Good, now let's see where the Vellum source node refers to. Look, inside the cloth geometry was created the Vellum constraint node, which defines the type of Vellum and to which refers the Vellum source. About Vellum constraint, we will soon talk in great detail. For now it is worth mentioning that its properties specified the cloth type. So now let's run the animation and see what we got. As expected, clothes fall under the influence of gravity. Now let's add some collision geometry to make the simulation more interesting. Let's call it collision. I will lower it down so that the cloth falls on it. Let's also change its orientation, increase the height decently, scale the radius a little, and check the end caps option. Well, all we have to do now is set it as a collision object. Good, now let's take a look at the DOP network. See, Houdini automatically created all the necessary nodes for the collision. So, let's play again. As you can see, there is a collision. Well, now I suggest adding to this the other type of Vellum, for example hair, or more correctly dynamic curves. For that let's create an empty geometry container and call it conditionally hair, then dive into it. So here, I will drop down the draw curve node just to create a few curves. Let's change the projection plan and start to draw them. Excellent, I also want to resample them to reduce the number of points. Looks good, now we can turn them into the hair. I'll use the shelf tool again. Since the curves are already selected, you just need to click on this icon. Here we go, in addition to the cloth source, the hair source node was added in this setup. If we look inside the hair geometry, we will see that was again created the Vellum constraint node, but this time it has a hair type assigned, therefore its properties are slightly different, but in general, it is very similar to cloth properties. Okay, now let's run the simulation and see what we get. As you can see, the curves became dynamic, and of course they interact with the cloth. Well, now I propose to add to these the balloon and grains. Let's again create an empty geometry container, then duplicate it. The first one, let's call balloon. The second one will be grains. So now let's dive into the first one and create the balloon geometry. Let's move the torus up. Then increase a little the columns and rows. Good, now let's create the geometry for the grains. I will use the sphere. Let's move it over the torus. Like so. Then add them to dynamics. Click on this Vellum balloon icon, select torus, and hit enter. Good, now let's create grains by clicking on this icon, selecting the sphere, and hitting enter. Here we go, now in the dynamic setup, has added balloon and grains. Now let's check what constraints were created for both. Look, inside the balloon geometry were created two vellum constraints. For the first one, the type of cloth is set, and for the second one, the pressure type is set. The combination of these two constraints is necessary to solve balloon type dynamics. And finally, let's check the grains container and move on. Here was created the vellum configure grain node, which configures the incoming geometry to be solved as grains in the vellum solver system, and since this option is checked on, it also creates points by filling the volume with the incoming geometry. So now let's run the animation and see what we get. That's it, all these different types of vellum interact with each other. Let's see it again. Well, we can move on. Now let's dive into the dynamic network. So, since vellum is particle-based, you can apply pop forces, and it also respects particle streams. Look, in this case we have 4 streams. That is, we have the ability to apply force on any of them separately, and the force will only affect that stream. So, for example, let's apply a wind force only to the hair stream. Add a little bit of noise, as well as directional wind along the x-axis. Now let's check the result. As you can see, the wind only affects the curves. If we take off from here and put it to the balloon stream, then will only affect the balloon. Here you are. In case if you want the wind to affect them all, then you need to put it after the merge node. That's it. They are all under the influence of the wind. Good, because in the future I will not use this approach of working with vellum. I suggest not going further. The disadvantage of this method is that you need to jump all the time from the dynamic context to the SOP context to set material properties. The output is also in a different place. Now I will show you where. Look, here is the output of the simulation. Now let's quickly go over this setup and conclude this lesson. So, this imports only the vellum geometry. And this one already imports the vellum constraint primitives. And they are both go to the vellum IO node. The vellum IO node is designed to streamline the common operation of packing a vellum stream, saving it to disk, and giving an option to use the saved sequence rather than the live sequence. So, if we look at its settings, we will see that it just file cache node. The only thing worth noting that in the Save Filter tab, a set of attributes are specified that are used during the calculation of the dynamics, but for further work, they are absolutely unnecessary and they all will be removed before caching. Okay, now let's check the number of primitive attributes before vellum IO node and after. See, there are 21 primitive attributes. Now let's check here. As you can see, they have already become 8. So, the last node is a vellum post-process SOP which provides common post-processing operations for vellum solvers. It can fuse the welds to be shared points, smooth the geometry, subdivide the mesh and so on. In addition, if constraints are provided, it can visualize the constraint energies, very useful when inspecting a simulation that has been saved to disk. Okay, that's probably all I wanted to say about this approach to setting up the vellum. And that's where I suggest ending this lesson. In the next lesson, I will already show you the second approach, when we will build vellum only in the SOP context, and all subsequent lessons will also be based on that approach. See you in the next lesson.